Hello, my name is David and I am a Maths PhD student studying at University College London. This is the first in a series of videos exploring the world of mathematical problem solving. In the first two videos, we're going to talk about some very general problem solving techniques. Indeed, so general that they apply to a wide range of problems we may come across in our everyday lives. Thereafter, we are going to explore a whole range of very specific mathematical problem solving techniques, including using invariants, using induction, and extremes. Each technique will have its own mini-series of videos. In each video, I'll talk about a problem solving technique and set you some problems where it may be useful to apply that technique. All of the problems have been chosen to be fun and interesting, and you should really have a go at trying to solve them yourself. You can use the comment section below the video to post your solutions or even just your ideas about how to approach the problems. I'll then talk about how you might approach the problems in the next video. It's important to remember that problem solving, whether in maths or any other subject, is difficult, and it's difficult for everyone. You only get better with time and practice, and even experts are constantly developing and updating their skills. Even though we're going to be looking at a lot of specific problems throughout these videos, the details of those problems are ultimately of less interest to us than the underlying mindset of how you go about solving a difficult problem. For the same reason, we're going to be less interested in the final answer to the questions, although that will be the cherry on top, and more interested in how we get there. When you're faced with a difficult problem that you don't know how to answer, or even how to get started, the most important things are to approach it logically, not to be afraid to make mistakes, and to be inventive in what you try. These principles are all you need to be a good problem solver. So in these videos, we shall be trying to formalize and develop these principles in the mathematical context. Without any further ado, let's get into it. There are 5 general problem-solving techniques that I want to talk about in this video. Most of them may seem very obvious and simple. However, when put together, they form a formidable arsenal which can be very useful when solving problems. Technique number 1. Get your hands dirty. Often, the best thing to do when you are faced with a difficult problem is to just get stuck in and try some examples or see what happens in special cases. For example, if we have the question, what is the sum of the first n odd integers? We can try out the first few values of n and see if we can spot a pattern. For n equals 1, we just have 1. For n equals 2, we've got 1 plus 3, which is 4. For n equals 3, we get 1 plus 3 plus 5, which is 9. And for n equals 4, we get 1 plus 3 plus 5 plus 7, which is 16. What do you notice about the numbers 1, 4, 9 and 16? Well, they're the first 4 square numbers. This is not enough to say that we have solved the problem, but it's a good start. And it also allows us to use our next problem-solving technique to make conjectures. Conjecture is just a fancy maths word for a guess, but not any old guess. We can only call a guess a conjecture when there's reasonable evidence to think that it might be correct. Making conjectures is very important because you can't try and prove that something is true until you have an idea of what it is that you want to prove. Sometimes you'll make conjectures which turn out to be wrong, but this is not a problem. Showing that a conjecture is wrong is progress of a different sort, and understanding why an idea doesn't work can often point you in the right direction to find the correct answer. In the example of summing up consecutive odd numbers, having got our hands dirty and tried out a few cases, we might reasonably guess, or conjecture, that the sum of the first n odd numbers is n squared. Now that we have a conjecture, we can try and prove it. Often, for this problem, people will use induction to prove it. Induction is the topic of some future videos, so for now, let's try and prove the conjecture without induction. Problem-solving technique 3. Draw pictures. Drawing pictures is one of the most important techniques in any problem solver's toolbox, and not just for problems in geometry. Pictures can help summarize the information in a long, wordy question. They can reveal patterns which aren't initially visible. They can help give you an intuition for what is going on in a problem, and they can illustrate the ideas of a proof. However, with great power comes great responsibility, and you have to be careful when using pictures. A bad picture can hinder and sometimes even mislead you, and a picture on its own cannot prove anything. How can we use a picture to help us prove that the sum of odd numbers is a square? We can represent a number x by a rectangle 1 by x. Putting together the rectangles for the first n odd integers, 1, 3, 5, up to 2n minus 1, we can use this staircase to represent their sum. Notice that two copies of the staircase fit together perfectly to form a rectangle. This rectangle has height n, because there are n odd numbers, and width 2n minus 1 plus 1, or simply 2n. Therefore, its total area is 2n squared. But as it was formed out of two copies of the staircase, we know that the area is also 2 times 1 plus 3 plus 5, all the way up to 2n minus 1. Equating these two expressions for the area and dividing by 2, we have shown that the sum of the first n odd integers, 1 plus 3 plus 5, up to 2n minus 1, is indeed n squared. Or in other words, our conjecture was correct. Problem-solving technique 4. Work backwards. If you know what you're trying to show, but don't know how to prove it, it can often be useful to start with the answer and try and work backwards. This is generally considered bad form when writing out a proof, but there's no problem in doing it to try and understand what's going on. Problem-solving technique 5. Restate the problem. Another really powerful strategy is to try and restate or reformulate the problem as a different but equivalent problem. This can help emphasize different aspects of the problem and so make finding a solution easier. We can use these two techniques together to try and solve our sum of odd numbers problem another way. Let's assume that we've tried out a few examples and conjectured that the sum of the first n odd integers is n squared. Starting from this, we can work backwards to try and reformulate the problem and prove that our conjecture is correct. Think about two consecutive square numbers, n minus 1 squared and n squared. If our conjecture is correct, then their difference will be the nth odd number, since writing out our conjecture for n squared and n minus 1 squared, almost all of the terms cancel and we are just left with 2n minus 1. But it's also true that if the difference between any two consecutive square numbers is the corresponding odd number, then it will follow that the nth square number is the sum of the first n odd numbers. We can write that the sum of the first n odd numbers equals n squared if and only if n squared minus n minus 1 squared is 2n minus 1. These two statements are mathematically equivalent. If one is true, then so is the other. If one is false, then so is the other. This means that we can restate the problem as, is the difference between any two consecutive square numbers the corresponding odd number? But now this question is very easy to answer with just a little bit of algebra. N squared minus n minus 1 squared, expanding out the brackets, cancel the n squareds, and you're left with just 2n minus 1. Working back through the logic, hopefully you can see that in this way we have proved that the sum of the first n odd numbers is n squared. To summarize, we have 5 basic problem-solving techniques. Get your hands dirty, make conjectures, draw pictures, work backwards, and restate the problem. I can guarantee that unless you're solving the most banal maths problem, you will have to use at least one of these, and probably several in conjunction. You should always have them at the back of your mind when you're presented with a problem. Speaking of which, I have 3 problems for you to try yourself. Problem 1. Cutting chocolate. You and 14 of your friends are getting peckish, so you offer to share a bar of chocolate with them. Fortunately, you have a 3x5 bar of chocolate on you. That means 1 square each. Your friends are getting impatient, so you want to break up the bar of chocolate into individual pieces using as few cuts as possible. Each cut must be a straight line across a whole piece of chocolate, and you can't stack pieces of chocolate to cut several at the same time. What is the fewest number of cuts to break up the chocolate into 15 pieces? If you can get your hand on chocolate, or 3, this is a great problem to try out for real, and the best part is that you can eat your working out afterwards. Problem 2. A busy bee. Barry Benson is a busy bee with an important message to deliver to his queen. He enters the hive by a hole in the bottom corner, but the queen hangs out in the opposite corner of the hive. Barry would like to fly straight across to her, but the hive is full of frames carrying honeycombs, so he must crawl around the inside surface of the hive. What is the shortest path that Barry could take to reach the queen? Problem 3. Hilbert's Hotel Hunt. Hilbert is a very hard-working hotelier and owner of a most hospitable hotel. It has an infinite number of rooms, numbered 1, 2, 3, 4, 5, and so on. Unfortunately for Hilbert, he has an infinite number of bookings, each with an infinite number of guests. On the first night, there's a guest in every room, and in the morning they each leave the money for their stay on their bed. As you might imagine, Hilbert is too busy dealing with all of the guests to go around and collect the money before the next booking of guests arrives. These guests are quite picky and will only stay in even-numbered rooms. Moreover, they are a disreputable, and each finding money on their bed, they decide to leave early in the morning without paying and taking the money they found with them. When the third booking arrives, they insist on being placed in rooms numbered by multiples of 3. Now, if these guests find money on their bed, like the guest in room 3 does, they will abscond with the money and won't pay themselves. If these guests don't find money on their bed, like the guest in room 6, then they will dutifully pay up, leaving the money on the bed and think nothing more of it. This behaviour continues for each booking of guests in turn. The next night, the fourth booking stays in the rooms numbered by multiples of 4 and steal or leave the money based on what they find in their room. At the end of all this, an exceptionally old, exceptionally tired Hilbert wants to go round the rooms to collect all the money which has been left for him. Which rooms should he look in to save him checking every single bed? Put your solutions to any of these problems in the comments below, or even just your ideas about how to approach them. If you get stuck, you can check there for inspiration. Don't forget to subscribe to get notified about when the next video comes out, where I will discuss the solutions to these problems. Thanks for watching.